7:35, and I will share my screen. I will. I forgot to upload the assignment, but I will do it in a couple minutes. Yeah, but well, I will discuss the problem for today, and then I will upload the assignment. Okay, I will start the recording. Okay, so the recording is ongoing. So as you can see from the Teams, the topic for today is the voltage regulator and the Zener diode. Yeah, so we will handle the Zener diode today. Yeah, we will learn how to use the Zener diode. But before we will go to the exercises, yeah, I will do some short introduction to the Zener diode. Yeah, so the Zener diode was handled on the lecture. Yeah, am I right?
Yes.
Okay. Yeah, but anyway, I will do some short introduction to the Zener diode. We will start from the symbol. Yeah, so we will start with something simple. So first of all, the symbol of the Zener diode. Okay, so the symbol of the Zener diode looks like that. You know, sometimes you can find it like that also. So this is the Zener diode, the symbol of the Zener diode. And we will start from the characteristic. Yeah, we will start from the characteristic. So the characteristic of the Zener diode. So current, voltage characteristic. Voltage, current. Okay. So in the forward configuration, yeah, in the forward configuration. So I mean by forward configuration, I mean when the current flows in this direction. Yeah? So when the current flows in this direction, yeah, it is behaving like rectifier diode. Yeah, so there is no difference. Yeah, in the forward configuration, there is no difference. So it's behaved like rectifier diode. Yeah? So in the forward configuration, it looks like that. Yeah. Okay. Oh, okay. And here we will have around of the 0.7. Yeah. So it will behave like normal diode. Yeah, normal rectifier diode. But so the most common use of the Zener diode is in the reverse mode. Yeah, we are using the Zener diodes in the reverse mode. Yeah, so we are using them when the current flows in reverse in reverse way. Yeah, so when diode works in the reverse configuration, and when the diode is configured in the reverse configuration, yeah, so for the normal diode, yeah, so for the rectifier diode, so the diode blocks all of the reverse current. Yeah, so here we have this blue one is for the normal diode. Yeah, so normal diode will block the reverse current flow. Yeah, but the Zener diode, has the Zener voltage point. Yeah, so we have Zener voltage. Yeah, and this Zener diode, yeah, will of course block will block the current flow until we will reach the Zener voltage. And then it will start to conduct. Yeah. Okay. And here we have the Zener diode. So this is the characteristic for the Zener diode. This is for the Zener diode. Okay, so here we have the slopes. Yeah. So here we have the slope. Yeah. Here we have the slope, and here as well. Yeah. Because this characteristic looks like more realistic. Yeah. Because the ideal, when we want to model the ideal Zener diode, yeah, when we want to use the ideal model of the Zener diode or the rectifier diode. Okay, so here we have the voltage, here we have the current. So the ideal characteristic, yeah, will look like that. Yeah, we will have straight line here, yeah, and here we have Zener voltage, and here we will have, of course, straight line here. Okay. So the question. And of course, the diodes, yeah, are manufactured to have the different Zener voltage points, yeah. So they are manufactured in for the different Zener voltage points. Okay, now we will start with the application, yeah. So we will try to build a simple voltage. Oh, so we have the transformer, yeah. We have the transformer. Here we will have, let's say, 230 AC. Here we will have, let's say, 9 volts, yeah, AC as well. Okay. But this is not the task for today, yeah. This is not the task for today, what I'm showing now. It's just to have the view, yeah. Where we can use the Zener diode. This is just the example. Here we have the bridge, the rectifier, the full wave rectifier bridge. Yeah. Okay, we will use that. We will build them with the diodes. Okay. Okay. Here we will have, because this is the full wave rectifier. This is the full wave rectifier. Full wave rectifier. Okay, we will have here this voltage, yeah, this voltage here, yeah. We will have upper half waves, yeah. We will have upper half waves, yeah. 9 volts, yeah. Yeah. Okay. Okay, and we want to produce them. We want to produce the constant voltage. Yeah, we want to produce. Let's say we want to have the 5 volts of the constant voltage. Yeah, we want to. That's what we want to achieve. We want to have 5 volts on the output. Yeah, so we want to create some power supply, and we want to have 5 volts of DC voltage. Yeah, of DC voltage on the output. We want to have it, something like that, on the output side. Okay, but here we have only now, for the very moment, we have only the upper half waves. Yeah. Okay. Of course, we can reduce. We can fulfill those gaps, because here we have the gaps. Yeah. Of course, we can fulfill those gaps with the capacitor. Yeah. So when we will put the capacitor here. So when we will put the capacitor here. Yeah. Okay. Then of course we will have. We will fulfill those gaps with the capacitor. Yeah. So now the output will look like that. So we will have charged, now discharged, charged, discharged, charged, discharged. Yeah. So now we will have we will have something which is similar to them, and of course around of the 9 volts. Yeah. And now we will have something which looks like the constant current, but we have a voltage ripple. Yeah, here we will have the voltage ripple. Yeah, okay, V ripple. Yeah, yeah. So we have V ripple. We can also calculate that this ripple voltage from this equation. So this is I over the 2FC. Yeah. So this yeah. So this ripple. Yeah. Yeah, depends on the frequency and the capacitance. Yeah? So when we will put bigger capacitance or we will increase the frequency, we will reduce the ripple. Yeah. Okay. So this is I load. Yeah. So I forgot to mention that this is it depends on the I. Yeah. Okay. So here, this ripple depends on the I. And because of course, capacitor stores some energy. Yeah. And this energy needs to be used to fulfill this gap. Yeah. Okay. So this is the load current. And of course, we need to adjust this capacitor to some load. Yeah. Okay, but still we have some ripples. Yeah, and we want to have the constant 5 volts output. Yeah, so we want to have the constant 5 volts output, and now is the place for the voltage regulator. Yeah, which we can build with the Zener diode. Yeah? So now we will build so we have R and we have Zener diode here. Okay, so now we have R and the Zener diode. And this is the place for the voltage regulator. Yeah? So this thing here, okay, yeah, is the voltage regulator. Is the voltage regulator. Of course, you can connect the voltage regulator now. Okay, and then we will have some load. Yeah, here we will have some load, resistance load, which will be connected to our voltage regulator. And now, how it will work? Yeah, we can see that this Zener diode is configured. Yeah, is configured in the reverse configuration. Yeah, okay, because here we will have plus. Yeah, so here we will have plus. Yeah, so this. Yeah, so in between those 2 points. Yeah, yeah, we will see something like that. Yeah, so something is some voltage with the ripple around of the 9 volts. Yeah? So it will be always around of the 9 volts here, and here we will have the ground. Okay, so we will see. Yeah, so this Zener diode is configured in the reverse mode. Yeah? So we are using this part of the characteristic. Yeah, we are using only this part of the characteristic. Okay. Okay. So now let's. Here we have the R. Here we have Zener diode. So let's try to analyze it, yeah, a little bit. So we have 0 volts here. So what will be the output now on the Zener? On the Zener, so this is the input voltage, V input voltage is equal 0. So output voltage in our case. So here we have the output voltage, V out. Here we have the V in. So now we want to draw the relation between those two output voltages. Yeah. So when we will have the 0, of course, yeah, then we will have 0 volts on the output side. Yeah. So when we have 0, we will have 0 volts. Yeah. Okay, 1, 2, 3, 4, 5, 6, 7. Yeah. Okay, and let's say this Zener diode which we are using is has UZ Zener voltage around of the 5 volts. Yeah. Okay, so now when we have 0 volts, of course we will have 0 on the output. When we will have 1 volts, yeah. When we will have 1 volts now, we will also have 1 volts on this side because this is the less than the 5 volts, yeah. And this ideal, let's say ideal diode will not conduct, yeah, will not conduct because it's less than the Zener voltage, yeah. So when we will have 1 volts, yeah, on the output side, we will have 1 volts as well, yeah. We have 1 volts as well. Okay, 2 volts, this same situation, yeah. 2 volts, 3 volts, yeah, this same situation, yeah, is less than the Zener voltage, yeah. 4 volts, yeah, until we will reach 5 volts, yeah. Okay, so we have 5 volts now, and this diode will start to conduct, yeah. Now the diode will start to conduct. Okay, and as we can see, yeah, for the ideal one, yeah, it will start to conduct any value of the current, yeah, any value of the current. So if it's conducting now, so when we will start to increase the voltage, yeah, so the voltage will remain on this same level, yeah, always will remain on this same level. So we have 5 volts of this Zener, yeah? Vz equal to 5 volts. Okay. Okay. So we will. So let's say we will start. So the output voltage on this so the output voltage on the Zener will remains on this same level. Yeah, on this same level during the whole time. Yeah? For the ideal Zener diode, of course. For realistic solution, we have the slopes. Yeah, here we have the slopes, which depending on the internal resistance, and of course we will have slight change of the voltage. Yeah? We will have slight change of the voltage with the current increase. Yeah? Okay. Okay, so we will see. Yeah, so as you can see, yeah, when we will start to increase the, the input voltage, the output voltage will remain on this same level. But now is the question for you: why do we have this resistor here? Do you know why do we have this resistor here?
To have a voltage divider.
Yes, exactly. Yeah. So this is the kind of the voltage divider then, yeah. So what will happen? Yeah. So if the Zener diode, yeah. So what if we have the situation that we have 12 volts here, yeah, and then we have the Zener diode connected in this configuration, yeah. Okay. So we have the Zener diode connected like that. And this UZ is equal to 5 volts, yeah. Okay, so this is so for the ideal components, we will break the Kirchhoff's law here, yeah, because yeah, so those two voltage drops should be equal, yeah, but we cannot equalize them because yeah, this voltage drop for the Zener diode is equal to 5 volts. Yeah, but this is only for the ideal component. Yeah, in the real situation. Yeah, in this real situation, this Zener diode has some internal resistance, internal series resistance. Yeah. Okay. Okay. This is of course the. So this is the Zener diode. Yeah. So this resistor which is internally. So this resistor is inside of the diode. Yeah? Okay. Okay. So then here we will have 5 volts, and this will be the rest. Yeah. So in this case it will be 7 volts. Yeah. So 7 volts will be the voltage drop on this Zener diode. Yeah. So without this resistor, yeah, we can burn the diode. Yeah, we can burn the diode because all of the heat, yeah, will be inside of this Zener diode. Yeah, because here we have this series resistance with the voltage drop. Yeah, but when we will introduce this resistor here, then this voltage drop, yeah, this remaining one. So this in case of this 12 volts and the 5 volts here. So this 7 volts will be here, yeah, on this resistor, yeah. And then we can adjust the power of the resistor, and then we will not burn the diode, yeah. So in this case, okay. Okay, and now what is your first task for today? Yeah, or what is your first task of today? Okay, so you need to put in the Tinkercad, you need to create this kind of the circuit. Yeah? So R, and then the Zener diode. Yeah, so you need to place the R and the Zener diode like that. Okay, and you need to configure because in the Tinkercad you can configure the Zener diode. Yeah, so you need to use the UZ equal to 4.7 volts. Yeah, equal to 4. To equal, so you need to set this Zener diode, the Zener voltage of this diode to 4.7 volts. Yeah? And you can use the resistor which is equal, let's say, 1000 ohms. Yeah, so 1000 ohms. So you need to build this circuit. Yeah, 4.7. Okay, and what is your first task? You need to measure the characteristic of the diode in this with this circuit. Yeah, so you need to exercise number 1 is to measure this current voltage characteristic. Yeah. Okay, so exercise number 1 is to measure the current voltage characteristic. But how we can measure the current voltage characteristic in this equation? Yeah, in this circuit. Yeah. So we need to put the amperometer here. Yeah. So we need to put the amperometer here, and then also the voltage meter here. Yeah. Okay. Here we need to connect the power supply. Yeah. So we need to power supply connect. Power supply component here, of course. So it will be plus and it will be minus. Okay, plus minus, and then you need to produce the ramp. Yeah, so you need to produce the ramp here, ramp of the voltage, yeah, from 0 to up Vmax, with of course some step, and then when you're increasing the power supply voltage, yeah, you need to each of the steps you need to measure the current, yeah, and then the voltage, yeah. Because in this configuration, the same current flows through the resistor and through the Zener diode, you know, in both of the cases. Yeah. So this current is common for both of these elements. Yeah. And this is the Zener voltage. Yeah. So EZ and the UZ. Yeah. And when you will, then you need to just plot all of this data. Then you need to plot just all of this data. and you will see something like that. Yeah, so this is the use it. So here we have the voltage, here we have the current. Okay, so it's so far clear to you. What is your first task?
Yes.
Okay, so I will also share you the Tinkercad. Okay, so basically you need to create. Can you see the Tinkercad?
Yes, we can.
So basically you need to create the circuit like that, yeah. And so with the power supply, and then we can see how it is changing, yeah. And you need to, for each of the measurement point, you need to take the measure of the current and the measure of the voltage. Yeah? Of course, you need to configure the multimeters. Yeah? So this is your first exercise. And why we are doing that? Yeah, why we are doing that? Because then we will have the characteristic of the Zener diode, and your next exercise. Yeah, so exercise number 2. So the exercise number 2 is to create. Yeah. So in the exercise number 2, we will have the 9 volts here. Yeah, we will have 9 volts here. We will have the resistor. We will have the Zener diode. Yeah, so UZ is equal 4.7 volts. So we will use this same Zener diode in the exercise number 2. Yeah, but then we will connect. Then we will connect the. Then we will connect the 5 kilo ohm resistor. Then we will connect the 5 kilo ohm resistor. And your task in the exercise number 2 will be to find the R value. Yeah. So RD, let's say RZ, let's call it RZ. So you need to find the RZ value. Yeah. In the exercise number 2, when we have the 5 kilo ohms load. Yeah. Okay, and do you have any questions according to second exercise? So in the exercise number 1, you need to plot the characteristic of the Zener diode in the exercise number 1. In the exercise number 2, we will use the same diode, but now we have the load. Now we have the load, and we have 9 volts of the power supply. So it is supplied from the 9 volts. And we want to have the 5 volts on the output. Yeah, we want to have the 5 volts on the output. Okay. So now we need to adjust this resistor value to have the 5 volts on the output side. And do you know how we can find this resistor value? How can we calculate this resistor value when we have circuit like that?
I would say we have to treat the Zener diode and the 5 kilo ohm resistor like parallel resistors, and like connect them together.
But they are not connected in parallelly, yeah, with this R2. Okay, so the solution for that is simple. So this Zener diode is connected parallelly with the resistor. Yeah? So the Zener diode is connected parallelly with the resistor, and we want to have 5 volts. Yeah, and we want to have the 5 volts. We will take a look into the characteristic, yeah, because we will measure the characteristic in the exercise number 1. So we will find this that the characteristic, yeah, so it's Vz is equal 4.7, okay, and this is here we have the slope, yeah. So we will have 5 volts at some point, yeah. So here we will have 5 volts at this point, yeah, because we have the slope on the diode, yeah. Because we have the slope on the diode, okay. And this 5 volts, yeah, we will have when we will have some specific value of the current, yeah. Alright. So we have the 5 volts here, and then we will have the Zener current, yeah. Okay. So we will have 5 volts when some specific current will flow, yeah. Okay. So this which you will read from the characteristic, yeah? So because here we have current, here we have the voltage. So you need to find this value from the characteristic which you will measure at the exercise number 1. Okay, then when this current will flow through the diode, yeah. So when this current will flow through the diode, yeah, then this voltage drop on the diode. Then this voltage drop on this diode will be equal to 5 volts. Okay, and that's what we want to achieve. Yeah, that is what we want to achieve. Yeah. Okay, and when we have the 5 volts here, we will also have the 5 volts on the resistor. Okay, and when we have the 5 volts on the resistor, through the resistor will flows also the current. Yeah. So we will also have the resistor current, and this resistor current, yeah, is equal to it will be equal to the 5 volts according to the Ohm's law over the 5 kilo ohms, yeah. So it will be equal to 1 milliamp, yeah. Okay, so that means this resistor current is equal 1 milliamp now, and here we have the point. Yeah, according to the first Kirchhoff law, so we have I. So let's say it's just the I, which is equal IZ plus the IR. Yes, and then when we have the 5 volts on the Zener diode, so the rest, so the 4 volts will be on the resistor here. Yeah, so now the Zener resistor, yeah, will be equal to 4 volts, yeah, because the Ohm's law. So the 4 volts divided by I Zener plus IR, yeah, and that's how you can find the resistor value. Yeah, it's clear to you?
Yes.
Okay. Okay. So we have 2 exercises for today. Yeah. So we have like one more hour. So the deadline is as always the 1 week. Yeah, but you can try to finish it today. If you have any, I will share this whiteboard with you. Yeah, I will share this whiteboard with you, and I will also upload the instruction for today. But so what do you need to provide to me today? So the characteristic of the diode, yeah, when we have the Zener diode equal to 4.7, of course you need to measure it, yeah, and you need to configure it in the Tinkercad. So when you will click on the diode, you can change the Zener voltage. So in your case, you need to put 4.7, yeah, of the voltage, Zener voltage. And you need to measure the characteristic. Yeah. If you want, you can measure the full characteristic. Yeah, because this is only the reverse configuration. Yeah, so in the reverse. But if you want, you can also measure in the forward. Yeah, in the forward configuration, it will be just for you. So if you want, you can measure also the forward. So we will have 0.7 here. Yeah, then. But if you want, yeah. So if you want to measure the forward configuration, yeah, so you need to change the power supply. Yeah. So in this case, here you need to put the plus, and here you need to put the minus. Yeah. Then you can measure it in the forward configuration. Yeah. But you will see that it will behave like a rectifier diode. Yeah. Okay, so in the first exercise you need to measure the characteristic. Then in the second exercise you need to use this characteristic to create the voltage regulator for some specific load. Yeah? Okay, this is called the simple voltage regulator. Yeah, because here we have some problems. Yeah, because this RZ, yeah, so this RZ, yeah, is connected with the 9 volts and the load. Yeah, so every time when the load will change or the supply voltage will change, yeah, we need to find the resistor value. We need to always change the resistor value. But in the real life, there is no possibility to change the resistance, to adjust the resistance, and we are using some kind of the enhanced version of this voltage regulator. So we can use the transistor or the op-amp with the transistor, but we will do it later when we will learn something about the transistors. Yeah. Okay. Okay, so we have 2 tasks, yeah? So task number 1 is characteristic. Second task is you need to use this characteristic to calculate the RZ for those specific supply voltage and some specific load. Okay, so do you have any questions to the exercises?
I guess not.
Okay, so I will also show you. Some real-life example as well, because this is the simulation. But when we will go to the shop, we can also buy the Zener diode. Yeah, we can also buy the Zener diode. Okay, can you see my screen?
Yes, we can.
Okay, and this is the example characteristic from the datasheet. Yeah. Okay. So this is the example characteristic, and as you can see here, we have in this row, in this type row, yeah, in this type row, we can see that actually this nominal voltage. Yeah, here we have Zener nominal voltage. We have different Zener diode type, different Zener diodes. Yeah, so the diodes are manufactured to have different voltages. Yeah, so we can have 2.7, 3, 3.3. 3.6. So we have different values of the Zener voltage. Yeah. Okay. And when we will buy the diode, yeah, so in the data sheet normally the characteristic is not included. Yeah. So when we will scroll here, we cannot find the characteristic for the Zener voltage. Yeah, because yeah, it will be too many of them. Yeah, in the document. Yeah. But we have usually we have the table like that, yeah. So we have the table like that, okay, and I will copy paste it here. So in the real life, when we are designing the voltage regulator, we only have this table, yeah. And how to use this table? Yeah. So let's say we want to design the voltage regulator to have 3.3 volts. Yeah. So we want to design the voltage regulator which will have 3.3 volts on the output side. Yeah. So of course we will use this diode. Yeah. So we will use this BZX85C and then 3V3 volts. Yeah? So we will use this diode, this Zener diode, and what we can and how we can use this table. Yeah, because here we can see that this 3.3 volts. Yeah, so this VZ is equal 3.3 volts when we have 80 milliamps. Yeah. So when we have 80 milliamps. Okay. So when we have 80 milliamps. So when we will have 80 milliamps current, yeah, then the voltage drop will be equal to 3.3 volts. Yeah. So let's say here we have the resistor. Here we have our Zener diode. Okay. So we will have, when here we will have 80 milliamps, then the voltage drop will be equal to 3.3 volts. Yeah. And of course, when we will connect some load, yeah. So for example, when the load will be equal, let's say 100 milliamps. So our load current is equal 100 milliamps. Then through this resistor will flow 180 milliamps. Yeah. Okay. And when we will have a situation like that, we will always have 3.3 volts. Yeah. In this situation. Yeah. Okay. So do you have any questions? Maybe according to this table, because as you can see, we have different rows here. Yeah. For example, we have also the resistance. Yeah. So we have some kind of the resistance. Yeah. Because this resistance inside of this diode, inside of this Zener diode, this internal resistance, this series resistance, which I mentioned at the beginning. Yeah. This is not linear, yeah. So it's not linear resistance. It's non-linear, and here we have two test conditions, yeah. So when we have 80 milliamps, so when we have 80 milliamps, so this resistance is less than 20 ohms, yeah. So this RS is less than 20 ohms, yeah. Okay, but when we have small current, yeah. So when we have like small current, like 1 milliamp. Yeah, so when we have 1 milliamp, instead of the 80 milliamps, we have 1 milliamp. So then this resistance is equal, as you can see, 400 ohms. Yeah. Okay. Okay. And here we have also the reverse current. This column here. Yeah. Okay. This column here is because yeah, I will show you on the characteristic. Okay, so this is the forward configuration, and now it's the reverse. Yeah. Okay. Okay, Zener voltage visit. So here we also have some current. Yeah. So small current is also flows here. Yeah. So this so at 1 volt. Yeah. At 1 volt, yeah, we can see that this current is less than 100 microamp. Yeah. Okay. And also we have some temperature coefficient because also the resistance of the semiconductors is changing with the temperature. Yeah. So when the temperature change, when we have the temperature change, then of course the resistance of the semiconductor is also changing. Yeah. So do you maybe know what is the relation between the temperature and the resistance in the semiconductors? So when the temperature rise, yeah. So in the semiconductor, of course, yeah. In the semiconductor, well, so when the
drops.
So resistance goes down, yeah, exactly, yeah. So it's opposite like in the passive elements, yeah. So when we have like regular resistor, so when the temperature rise, yeah, so also the resistance rise, yeah. But in the semiconductors, when the temperature rise, yeah, then the resistance goes down, yeah. Okay, this is the connected with the because in the semiconductors we have the pairs, yeah, electron and the holes, yeah. We have the pairs electron and the holes, yeah. And then when the temperature rise, then we are increasing the movement, yeah. So we are increasing the movement. So we actually the temperature is the energy, yeah. So the temperature is the energy. So we are we are supplying the semiconductor with some additional energy, thermal energy, and we are increasing the movements of the free carriers. Yeah, and when we are increasing the movements of the free carriers, then of course, so the current can easily flow. Yeah, when we have high movements of the free charges. Yeah, so that's the relation. Yeah, so that's how it's connected. Yeah, because the temperature is an additional energy, so we are increasing the electron and holes movements. Yeah, so the current can easily flow. Yeah, it's clear what I said.
Yes.
Okay. Good. So the task for today is clear for you. I will leave this meeting, but I will stay online. I will stay online. So if you need some help from my side, just make a private chat with me, and then I will help you. Yeah? Okay. I will stop the recording. Okay. I will. So the deadline for that is till end of the. And so till next Monday, yeah. So Monday midnight is the deadline, yeah. Okay, I just stopped the recording. So I will leave this meeting. But if you need to discuss something with me, so just make a chat with me, and then I will help you. Okay. Yeah, we have like 40 more minutes. So if you need some additional help, just let me know. Okay. So thank you for today. And I will upload the assignment as well.
Goodbye.
Okay, bye-bye.